Welcome. The purpose of the video is to show step-by-step application of NARDL adding, and as we can see, this is our normal Eviews environment. This is the work file. In the work file, I have three variables: LE, LF, and LP. The two other variables or the objects in the work file are the constants and the residual placeholders. And this particular application, what we want to do is to make the LF our dependent variable, LE and LP the independent variables, and as such, I'm going to click LF first, and then LE and LP in that order. And I will now open as equation. So I go to equation now. It's been opened, and as we can see, we have LF first, LE, LP, and C. But this is not the environment we want to estimate our model. You can see this is LS, which is for least square estimation method. We need a RDL or RD environment to do that. In order to do this, we scroll down from the drop down and we go to ARDL. You can see it there. Pick that environment. So automatically the environment changes and we have a new dialog box. In the new dialog box, we'll see that our variables have been listed and there is no constant added. Don't attempt to put constant there. It's not needed. Automatically that will be fixed by the ARDL itself. Now, I want to keep the default setting, but you can change as you like. This particular setup, this is our indeterministic values: none, restricted constant, constant, restricted trend, constant, and trend. But in this setting, I'm keeping the default setting. Again, you can play around the different options here. The values of your selection criteria. We have AIC, SC swatch criterion. We have an Aquin criterion, and so. But again, I'm going to keep the default. So I go back to now. I have this setting. This first step, I estimate my adding model. ARDL is estimated. So this is the estimation. Very simple. As you can see, the model has been estimated. We have our dependent variable LF as desired, and then we have the two independent variables LE and LP. The dependent variable is of second order, so order 2. The independent variables are of zero order, 0 and 0 here. Now, this is the normal ARDL estimation, and of course, you can carry out all the estimation pertaining to this, all the analysis pertaining to this estimation. Now, for example, you may want to generate some, maybe long run. You have it here. You can also come back and say, okay, let me see the restricted version of this model, that is ECM form. We have it here. Now, this is not what we want to do now. What we want to do is to use this as a channel to our NARDL model, non-linear ARDL model. In order to do this, we need to instruct Eviews through the heading what to do. In order to execute this, we can go to View on this active equation table. We come here from View, we go to Label, and this is where we are going to instruct this. Click on Label, and then we have this view of the model. Here we simply type in the keyword, which is ASYVARS as well, and directly under value you put your treasured variables, those variables that you want to decompose, and they must be the independent variables, like in this example now, LE or LP, or 2 together, or if you have more than that, you can as well include them. But don't forget that there could be a problem of proliferation of parameters, so you have to be careful by the time you are adding more and more variables to this model. But in the example we are giving, we are still okay, because we have 293 observations, and then we have 3 variables, 2 of them the independent variables. So I will type my variables to be decomposed, LE and LP. Now, after I've done this, why this page is still active, why this equation is still active, I can simply go to adding. I presume that you have already downloaded and installed adding version. Adding on your computer. So if you have done that, these 4 items, make nonlinear ARDL, make testable form, NARD multiplier graph, NARD cosine and cosine Q graphs, all of them will be listed for you. So if you have them this way, then the next thing to do is to make non-linear ARDL. That's the first thing to do to proceed to transit from regular ARDL to non-linear ARDL. So we click on this. Now it has been generated for us. If you didn't specify, like we did here, you didn't specify this, then there will be an error. Okay, so in order to avoid that, you first specify this before you transit to the non. Now you can forget about this one for a while, you don't need it again. We come here, this is the page we want to analyze. Let me take this step by step. You can do all sorts of things you normally do with your ARDL here. For example, I can have my long run form of it. This here is generated for me. I can have the restricted version of it, which is a ECM version of it. This is it. You can see they are here. Okay. And then you can do your band testing of a thing. Of course, band testing results will be reported for you. This is it. Okay. This is your band test. Now you can see here. Compare the upper and lower limits for the test. And so those are the things you can normally do. But we want to proceed beyond this level in order to do the unusual that we create this particular add-in for. And what are you going to do? After you have estimated this model, you can see, note this must be NARD. You will see there, NARD. The equation will be titled NARD. Just click on it and make sure that it is the active equation table that you have. Then from there, you can go to add-in again and do all the post-estimation analysis for your model. Here, we come here. One of them is we want to generate the NARD multiplier. Okay, NARD multiplier graph. So you simply come here. Why that page is, equation object is active. You click on it. It is estimating it, so you can be patient. That might take a while. So the graphs have been generated. The first one has been generated, then the second one too. So we have the two of them side by side. You can see them. Okay. So of course, these graphs are already listed in the work file. They are here. They are kept for you for further use. So you can simply close them. They are already in the work file, as you can see here. The two of them are here. Now, what are you going to do next? Note that the decomposed values for the two variables are here also. Okay, so let's go back back to our model, estimated model, the equation objects that we have. Now, what else can you do? You can generate the cosine graph. So as we did for the multiplier graph, you come here and then you move to, just scroll down to NARD cosine cube and cosine graph. So you click on it and then you have these two. They are automatically generated for you. Okay, and so you have them. I'm not going to interpret this particular model. All I want to do is to spell out the steps you will take in order to implement your whole model. Of course, you can see the anomaly here, so it's up to you to decide whether that's what you want or not. Again, the cosine and cosine Q have both been listed in the work file. You must save this in order to retain it for further use. So you can always do that by saving your work file so that anything that is dropped there will remain even after you have closed your work file. Now, what again can we do? We have seen two things that we can do with our NARD environment. Another thing you can do is to try to test asymmetric effects in this model. For example, looking at this output, we have our long run parts. The highlighted is the long run part of our model. This where you have D, which is difference, done up to this point, represent the short run part of the model. And what you want to do is to test either for long run asymmetric effects or for short run asymmetric effects. And you can even decide to do all these, both of them together, both the short and long run, so that you have what we call strong effect, strong asymmetric effects. I don't want to go further on that. So you can just get as much information as possible from the literature on those concepts. Now, looking at this, we want to get this environment and replicate exactly what you have here. The reason for this is that the view that you are looking at does not, even though it presents the coefficients estimation and the standard error, t value and p, you can't carry out word test on this because it is hardwired. A way out is to replicate the same output in another format. In this case, we want to replicate what we have here in OLS environment. So it is as simple as that. So you can do it manually in which case you just create a model that looks exactly like this, and then you have your dependent variable as change in LF, while this will be your explanatory variables loaded into your Eviews. But that might be tedious, so we have automated this in the NARDL environment. What you do is to click on this and make sure it is active again, then go to add-in. From there, scroll down to make testable form. Make testable form, which as I explained before, is meant to replicate the same view as you have here. So I click on this. Let's place them side by side for you to see the two of them. The two results are the same thing. The one from out there and the one from OLS are exactly the same, which means what we are doing here is not wrong. So we can put this one aside and use this one instead, and to test our hypothesis that we want. I will use one illustration. Looking at this, we have in our long run part of this model, we have this. We have long run for the positive component of LE, negative component of LE. We also have positive and negative component of LPs. Now, we might want to see the asymmetric effects in these long run parts, and from there decide whether we have asymmetric or not in our long run part of this model. I will first do for LE and later for LP. For LE, okay, let me mention this. To facilitate this analysis, it's good practice to make a representation of this, as you will understand later why it is important. Now, let's go back to our view output page. Now, looking at this represents the long run part of our model all the way up to these points. You know, these are variables without difference. So represents our long run part of the model. Now, the parameters are the placeholders. You have to be careful here. The positive part of LE is associated with the third parameter in the placeholder, the third value in the placeholder, and the negative component of LE is associated with the fourth value in the placeholder for coefficients, and so on. So what you need to do here is to go back to your OLS version that we created earlier, which is this, and go to view, and you can then move to coefficient diagnostic and over to what test coefficient restrictions. Here we click that, and then we look at what we want to restrict here. We are trying to restrict C3 and C4. So we type C3 equals to C4 equals to C4. Of course, it doesn't matter. It could be capital, or that is upper case, or lowercase, or little c. So this hypothesis is such that H naught is C3 equals to C4, which is exactly what we mean by asymmetric test for that component. Therefore, we click OK, and then we see the output here. What this output is telling us is that there is no significant difference between those two parameters. Indeed, this is confirmed by the p-value that we have here. This is our p-value, okay, and this is our t-value, and this t-value is generated by dividing our coefficient here, which is the difference between C3 and C4, okay, by the standard error associated with it. Okay, when you divide the value by standard error, then you have the t-value. Of course, we can also make use of this in this case because we are having just one value. So the probability or p-value suggests that there is no long run relation. There is no asymmetric effect in the long run. Now, let's look at the second one. Of course, if you want to report this, it is a good idea that you phrase it and drop it in your, maybe later you save it. But now, let's look at the second hypothesis, long run asymmetric effects in LP. So we come here again, we go to the restricted view, and then we type in our coefficient as before. But in this case, we are going to be looking at C5 and C6. C5 equals to C6. Now, let's see. Wow. Unlike the previous result, where we have not so much difference between the component, the negative and the positive component, in this particular one, we have the positive and negative component being significantly different from each other. In particular, the value is this, but you cannot judge by this. You have to look at the relative value with respect to the standard error, which is reported by the t-value here. And t-value large, bigger than before, and the probability is also suggesting that this is about 2%, let's say 1.4%, as you can see here. So this can be accepted as the confirmation of the asymmetric effect in the LP, unlike in the LE part of the model. So that is how to use that for long run tests. And of course, you might want to also test for the short run part of the model, which is very simple also to do. What you do here is to look at this. Note this is our LF, this is LP, this LP, this LP, this LP. All we see that, okay, LF in this case is only appearing once. That is difference of LF. LF is appearing once, okay, which is the dependent variable. But when you look at LP, we have this. So we have here, we have here. We don't have LE here at all. We don't have LE at all. And that is the nature of our the order of the model. So you don't have to be bothered about this. Of course, if the order is more than 0, it will appear there as one of the short run part of the model, which means there is no short run effect for LE, but we have short run effect for LP. That's why we have these results like that. But then our purpose is to test for the long run and short run short run effects, asymmetric effects in the LP. So we mark the positive values, which we have as 8 here. The others are just negative. So what we are going to do here is to set this 8 against the sum of this, or for the negative, the sum of them. So we have here our test as usual. I'm going to test for asymmetric here, and then we say okay, C8. Now C8, that is for the positive. You want to set it all equal to the sum of the coefficient associated with the negative part of LP. So it's a C9 plus C10 plus C11, and we have C12, okay, plus C12. So this is very simple and should be understood as such. We are simply setting the coefficient associated with the positive part with the coefficient associated with the negative part. And if we have more than one term for the positive part, then we will have it on this side. Okay, on this side. But in this particular case, we just have the only one term, which is this, for the positive part. But unlike that, we have many terms associated with the negative. So that's why we are having this. So this is our test of asymmetric for that. So we click on this, and again we can see that we have a significant effect. Okay, that is the long run and the short run asymmetric effect exists in this particular model. The short run asymmetric effect also exists for this particular model. As you can see, our p-value is less than 5%, and the result of our t-value is this, and this is the value of this sum together. Okay, we have this, we have the standard error, and that is how to go about using NARD to accomplish nonlinear ARDL model estimation. I hope you enjoy it. Thank you so much for watching. Bye.